And good morning. Thank you for joining our next installment of the DC-MUSE webinar series. Hopefully everyone can hear me and can see the slide that I'm sharing here. If you're new to DC-MUSE, I'd just like to briefly tell you a little bit about who we are and what we do. DC-MUSE is a center that brings together a diverse group of folks from both academia and industry across a wide variety of disciplines, whose work all focuses on catalyzing the decarbonization of the chemical industry and chemical manufacturing by utilizing increasing amounts of sustainably generated electricity. So that's what we're kind of focused on doing. We're supported by funding from the Sloan Foundation, so I'd like to thank them for their support. I'd like to thank all of you for joining this morning, and if you're not following us already, I would highly encourage you to please follow DC-MUSE on LinkedIn, so you can be alerted to when we share different information, and of course, as we continue to host this webinar series. We have two speakers today, Dr. Rajput from Stony Brook University and Dr. Zach Ulyssi from Meta. Just to give you an overview of how we're going to run our presentation, our webinar here today. Each speaker will give a 15-minute talk, and then after their two 15-minute talks, we will have a question and answer session at the end. Our speakers here today are going to be talking about modeling and machine learning for the design of electrolytes and electrolyte interfaces, again, all focused on electrification to decarbonize the chemical industry. Our first speaker is Dr. Nav Nidhi Rajput from Stony Brook University. So just to tell you a little bit about her and her work, she's an assistant professor in chemical engineering at Stony Brook. Her research focuses on multiscale computational modeling and materials informatics for electrochemical energy conversion and storage, with emphasis on electrolytes and solid liquid interfaces. She develops integrated frameworks combining density functional theory, molecular dynamics, thermodynamic modeling, and machine learning to enable data-driven molecular discovery. Professor Rajput is the creator of several open source platforms for high-throughput electrolyte simulations and spectroscopy-informed validation, with applications spanning CO2 electroreduction, batteries, and complex liquid systems. So Professor Rajput, please go ahead and get started and share your slides.
Okay. All right, can everyone see the slides?
Yes.
Okay, perfect. First of all, good morning, everyone. And thank you, Ian, for the kind introduction. I hope everyone can hear me fine and can see the slides. And if there are any interruptions, and there are any difficulties, feel free to interrupt me in between. So thank you so much for the opportunity to share our work today. It's truly a pleasure to be here and share some of our recent work on data-driven insights for electrolyte design and carbon dioxide electroreduction. And as we know, carbon dioxide electroreduction converts carbon dioxide into fuels and commodity chemicals using renewable electricity. And from an industry standpoint, this is attractive not only for emission mitigation, but also for carbon valorization, so converting carbon dioxide into a feedstock. However, for CO2ER to become industrially viable, the current systems must achieve a much higher Faradaic efficiency, high current densities, typically in the range of 100 to 300 milliampere centimeter squares, and long-term stability. And while there has been a significant work done on catalyst design, achieving these industrially relevant performance still remains a system-level challenge. And as we know that CO2 reduction reaction takes place at the EADL, along with the catalyst, the electrolyte design is equally important. And experimentally, we know that electrolyte play a very important role in controlling the performance of CO2ER. For example, CO2 solubility controls reactant availability. The identity of cations and anions stabilizes the key intermediates. And we know that water activity shifts the balance toward hydrogen evolution. And ultimately, it's the solvation environment and molecular interactions in the EDL that governs the overall CO2 selectivity. And despite the strong effect of electrolyte on the performance of carbon dioxide electroreduction, most of the computational models primarily focus on catalyst energetics and treat electrolyte effects implicitly. And this limits our mechanistic understanding of the molecular interactions and solvation structure and understanding how the solvation environment is controlling transport properties. So to address some of these challenges, we developed a hierarchical physics-informed framework to systematically explore a large chemical space of organic solvents and then quantify how molecular structures govern bulk electrolyte properties. So today I'll talk about how we integrated electronic structure calculations with solution thermodynamics, molecular dynamics simulations, and interpretable machine learning models to derive molecular design rules for carbon dioxide electroreduction. So to systematically explore the electrolyte design space, we built this hierarchical physics-informed framework that begins with a very large chemical space. So at the beginning, we start with over 1.3 million organic molecules extracted from different public data sets. And we first apply chemical and physical stability filters and selected neutral molecules with reasonable boiling point and flash point consideration to ensure phase viability. We next perform something called structure similarity screening and comparing the structures of these solvents with the ones which have already been tested in the literature and show good performance. And this reduced down our chemical space to around 3,200 solvents, on which we perform high-throughput DFT calculations to predict various electronic properties and Cosmos calculations to predict various thermodynamic properties, such as CO2 solubility and solvent viscosity. And all these properties are directly relevant and affect the mass transport, reactant availability, and as well as redox stability during electrochemical performance. Then based on the quantitative metric for each of these properties, we further screen down the chemical space to much fewer systems, and on them we perform more detailed classical MD simulations to understand the solvation environment and the effect of solvation structure on transport properties. In parallel, we also developed machine learning models for rapid property prediction across a broader chemical space. And all this information and simulation results are consolidated in an open source cosmic dataset for reproducibility in results and transparency in data sharing and for further community-driven exploration. So taken together, this pipeline provides overall a link between large chemical space, molecular level interaction, and transport relevant electrolyte behavior. So as a first step, we examine how the protic versus aprotic nature of solvent chemistry influences the two key properties which are relevant to industrial CO2 ER performance, namely viscosity of the solvent and CO2 solubility. Now, across all the solvents that we have in our data set, we found that protic solvents such as alcohol, amines, carboxylic acid, and amides overall have a much higher average viscosity compared to aprotic solvents. And this happens primarily because of the strong hydrogen bonding network observed in protic solvents, which results in a much stronger self-associating extended network and reduces the mobility and increases the resistance toward flow. Okay. The effect of this strong hydrogen bonding is also observed on CO2 uptake, where because protic solvents are strongly self-associated, they have much less free volume and accessible sites to bind CO2 and dissolve CO2. As a result, most protic solvents show lower CO2 solubility compared to aprotic solvents. So taken together, these trends indicate how hydrogen bonding, while chemically intuitive, is detrimental to both viscosity and carbon dioxide solubility. As a next step, we try to identify promising candidates which can show us the best combination of CO2 solubility and solvent viscosity. So we basically mapped all the screen solvents as a function of CO2 solubility and solvent viscosity. And here we can see that most of the candidates fall in the central region with moderate CO2 solubility and solvent viscosity, really offering no clear advantages. So we applied two quantitative criteria of solvent viscosity, less than 0.001 Pascal second, and CO2 solubility of more than 250 millimolar. And this reduced down the chemical space and give us 6 promising solvents shown here on the top left quadrant. Notice it is important to note that all these 6 solvents are aprotic in nature and belong to cyclic ether or nitrile classes. Okay. And this is this is in agreement with the results that we saw before, where aprotic solvents can show much better solubility and lower viscosity compared to protic solvents. Okay. All right, so next step, we examined the molecular level interactions between salt, CO2, and solvents using classical molecular dynamics simulations. And for consistency and controlled experiments, all simulations were performed using the same electrolyte composition with 0.1 molar TBABF4 salt, 0.1 molar CO2, and in each candidate solvent. And we simulated the newly identified solvents and directly compared their performance with the 20 solvents which are previously reported in the CO2ER literature and show good performance with some of the commonly used solvents such as acetonitrile and DMSO. And this enabled a head-to-head comparison of these newly proposed solvents with the state-of-the-art electrolytes which is reported in the literature. So we looked into the details of the solvation environment around CO2 in these different electrolytes. And here I'm showing you the radial distribution function of carbon dioxide with solvent. We also did similar studies with all possible interactions in the electrolyte, but the weakly coordinating TBA-BF4 salt, which we chose purposely, shows a very weak binding affinity toward CO2. And across all the solvents we considered in our data set, CO2 is primarily surrounded by the solvent molecule, where the first peak is observed at a distance of 4.5 to 6 angstrom across all the 26 solvents we studied. However, the peak height and the shape of the peak, which indicates the strength of molecular interaction between CO2 and solvent, varies across different chemical classes. Okay, so most of the protic solvents, such as alcohol and amines, they exhibit sharper and higher peaks at around 4.6 to 5 angstrom, indicating stronger and more localized coordination for CO2, primarily mediated through strong hydrogen bonding interactions. While these stronger interaction may appear favorable at the beginning, it can also increase local structuring and may hamper the transport properties in these protic solvents. In contrast to that, aprotic solvents, particularly cyclic ethers and nitriles, display broader and lower intensity peaks. And this reflects a weaker but more dynamic coordination environment driven by dipolar interactions instead of hydrogen bonding. So such environment may enable sufficient stabilization for carbon dioxide without excessively restricting transport. Overall, this result shows that the solvent functional group directly govern the strength and accessibility of CO2 in these electrolytes. And to understand how this solvation structure translates into transport properties, we next examine diffusion dynamics. And as expected, CO2 diffusivity decreases with increase in pure solvent viscosity, consistent with the classical Stokes-Einstein's relationship. And this is particularly important for CO2ER, where high current density is required rapid mass transport to the electrode surface. The 5-like cyclic ether, which are shown here on this red box, clearly stands out, which emerged from our screening, and they exhibit the highest CO2 diffusivity and also the highest solvent self-diffusion coefficient. We also observed a strong correlation in the diffusivity of CO2 and solvent, which indicates that CO2 is diffusing through a coupled motion with solvent together in the solution with the solvent matrix around it. Okay. And this indicates that solvation environment that is sufficiently stabilized but yet dynamically accessible could be more efficient for CO2 transport and will lead to better CO2 transport and less mass transport barriers. And while our DFT and COSMOS results provide accurate prediction of various properties, they can also be very computationally expensive, especially for when we are exploring a much larger chemical space. To enable rapid prediction of broader chemical space, we developed physics-informed machine learning models trained on our computed data set. And we focused on 4 properties directly relevant to CO2-ER performance, which are CO2 solubility, solvent viscosity, ionization potential, and electron affinity. And as shown here in the parity plot, the model achieves strong predictive performance for carbon dioxide solubility, solvent viscosity, and ionization potential. The R-square values are above 0.9. For electron affinity, we observed a lower predictive accuracy with R-square value of 0.66. And this is expected and has also been reported in the literature for other systems like battery, where electron affinity is more sensitive to molecular electronic structure and anionic instability, which leads to poor performance of machine learning models for electron affinity. But importantly, these models generalize well across diverse solvent chemistries, enable rapid property prediction without repeating the expensive quantum chemistry calculations. And beyond predicting different properties, we also try to understand why some solvents perform better over the others. So using SHAP analysis, we identify different key features which affect the targeted properties. So for CO2 solubility, and I know this, the keywords on the left-hand side are really hard to study, but these are the different descriptors, and we tested a very long list of descriptors, and this is just, just the top 10 descriptors that I'm showing here in this slide. So for CO2 solubility, we found that it is impacted primarily by the vibrational bond frequency, which is the stiffness of the OH and NH bond. And these high frequency bonds are signature of strong hydrogen bonding network observed in protic solvents, which again, reiterate how strong self-associating forces in protic solvent reduced free volume and accessible sites and limits the solubility of CO2. For viscosity, we found that the top features which control viscosity are the hydrogen bond donor group, vibrational frequency, and molecular size. So increased hydrogen bonding and molecular rigidity restrict mobility and increase viscosity. And this explains why smaller, weakly self-associating aprotic solvents, particularly cyclic ethers, shows the lowest viscosity. For ionization potential, the dominant contributors are Lewis basic sites and HOMO energy. So molecules with more donor atoms and higher HOMO levels are easier to oxidize, resulting in higher ionization potential, resulting in lower ionization potential. And for electron affinity, the SHAP analysis indicates that a more branched structure and lower LUMO energy level are capable of stabilizing an added electron and hence results in higher electron affinity. So importantly, across all the properties, the SHAP analysis indicates that hydrogen bonding and stiffness of OH and NH bond, along with larger molecular size, are the key factors which hamper CO2 solubility and increase viscosity in the solution. The frontier orbitals are primarily dominated by the HOMO and LUMO energies, along with the hydrogen donor groups and branching of a molecule. So weakly self-associating and electronically tunable solvents are more favorable for CO2-ER electrolytes. So as I mentioned, the results that I presented today are available as an open source database called COSMIC. So the high throughput calculations were performed using the infrastructure developed by our lab called MISPER, which allows to run high throughput DFT and COSMOS and MD simulations in parallel. And the cosmic database includes both the electronic and thermodynamic properties from DFT and COSMOS calculation, along with the ensemble properties computed using MD simulations. And it also includes the pre-trained machine learning models along with all the SHAP analysis that I presented today. Okay. All right. So just a quick note about where we are looking at in the future. And while some of the results that I presented today show clear molecular design trends, it is unlikely that a single solvent can meet all the desired criteria for CO2-ER electrolytes, from CO2 solubility to transport properties to interfacial stability. So we need to move from these single solvents electrolytes to most likely binary or tertiary solvent mixture, where for example the aprotic solvents can act as a primary carrier to stabilize the solvation environment along with providing better transport properties, and protic co-solvent can tune interfacial stability and proton availability. It is also important to incorporate interfacial molecular dynamic simulations to better understand the electrode-electrolyte interfacial reaction, which I think Jack will be talking about next. And finally, to design advanced computational spectroscopic analysis tools, which help us interpret experimental spectroscopic signature to probe the solvation and transport property even further. And with this, I want to show the most important slide and thank the student who worked on this project. So the computational infrastructure developed in our lab that work was primarily done by my former student, Rasha Atwi. And all the CO2-ER work that I presented today was done by my former student, Matthew Bliss, and my current student, Kuldeep Singh. And I would like to thank the funding from Stony Brook and ISCS for this work. And I'll stop here and, I can stop sharing my screen right, Ian, and so that Jack can start?
Yes.
Yeah, okay, perfect.
Thank you. Thank you, Dr. Rajput. Thank you for your great talk. And again, just as a reminder, we'll save the Q&A for the end. So I'll go right ahead and introduce our next speaker, Dr. Zach Ulyssi. He's a senior research manager at Meta's Fundamental Artificial Intelligence Research Organization, where he co-leads the FAIR chemistry team developing artificial intelligence and machine learning methods for materials, chemistry, climate technologies, and Meta's augmented reality and virtual reality hardware programs. He is also an adjunct professor of chemical engineering at Carnegie Mellon University and was previously an associate professor at Carnegie Mellon before joining Meta in 2023. He completed his PhD in chemical engineering at MIT and postdoctoral research at Stanford University, and his work integrates machine learning with quantum chemistry and molecular simulations to design novel catalysts and materials. So please, Dr. Ulyssi, go ahead whenever you're ready. Thanks.
Thanks, Ian. And I really like this order because now I don't have to explain CO2 reduction or what's important or any of the other things. Nidhi, you did an awesome job. Uh, Everything I'm going to talk about is open science. If you're not going to pay attention while I'm talking, at least go to the website fair-chem.github.io. All the papers, data sets, everything is available if you want to use it afterwards. Okay, so I thought I would give just a one-slide overview of what is FAIR at Meta. So FAIR is fundamental AI research. It's blue sky research, AI for the sake of AI, trying to move things as fast as possible. We have a history of being very open and reproducible, which is really great for doing open science. There's not just us in the science program. So there's also a brain imaging team. So there was a model, for example, called Brain to QWERTY, basically doing non-invasive scans of the brain to sort of understand how state-of-the-art image or language models and the architectures they learn might map onto the human brain. There's also been a lot of work on image segmentation models, for example, like the segment anything model. And even though that thing is very general and is being used in things like Instagram edits now, it's also really good for science. So if any of you are doing microscopy or visualizing electrochemical interfaces or anything else cool in that space, and you were doing your own image segmentation, stop, try some of the cool new generalizable tools. There's been a bunch of examples of papers now that have uses for all sorts of cool things, including places like Seagate doing grain boundary analysis for hard drives and other things. A lot of the packages that are developed at FAIR become useful for the entire community, things like PyTorch and Llama. And then there's our team, which I'll tell you a little bit about today. So when I was a postdoc, big data in catalysis was like a couple of hundred reactions. I remember doing all these calculations by hand. We were sort of building these databases on the fly. At Stanford, there was this project to basically get all the students to put all the things in one database. So every paper had to deposit all of their calculations. And that was state of the art. And that was about 2015, 2017 or so. And then when I moved to Carnegie Mellon, we tried to make some of this a little bit more systematic. Nidhi gave a great overview of all the cool things you can do with high throughput methods in the space. At the time, things were still like very, very, very preliminary. People didn't really even understand how to automate a lot of the things like enzyme replacement or how to systematically identify different catalyst surfaces. And so the first thing we did at CMU was try and get the data sets up to about order tens of thousands or so. So Soyin was a postdoc in my group. This was us. And then afterwards, a couple of other groups also boosted this up to order tens of thousands, which we thought was like quite impressive and big at the time. Around that time, I started collaborating with Meta, and we realized that actually the opportunity here was to try and make the models as generalizable as possible. And Nidhi was giving a really nice overview of all the cool things you can do with data science and machine learning to understand the properties that correlate with the experimental things that you care about. And that's one thing that you can get out of these systems. But also models that just work for replacing DFT are incredibly powerful, both for generating the sort of data that Nidhi was talking about and also for exploring new spaces. And it really was unclear at the time how far we were going to be able to go with the strategy. It was a bit of a shot in the dark. It was incredibly aggressive. It could have ended very badly. And so the first data set we built was OC20, named because we released it at the end of 2020. It was big. It was order 200 million individual DFT single points, orders of magnitude larger than anything else at the time. We didn't know how to sample surfaces, so it was really just random adsorbates on random intermetallics from the materials project, just a shot in the dark to see what was possible. And when we started, the models that were available were also not great. So Schnet and DimeNet were both really, really cool models in 2017. Really, really impressive given what was available. So kudos to them for releasing them. But when we tried to train on OC20, things like the adsorption energy, which is like the very first step in calculating reaction energies for catalytic pathway, the mean absolute errors were like 0.6, 0.7 eV. And like frankly, we were all quite worried because zero point 0.6 or zero point 0.7 is not very close to 0.1, which is sort of our goal down here, right? If I said, what do I need in order to make a microkinetic model? This is not sufficient. I need something down here. And so we also got a little bit worried that maybe we hadn't generated enough data, maybe we made some mistakes. Yeah, it was unclear what we needed to do. But fortunately, we were not alone in this, and there were many other people in the community who stepped in to help. And so these are all different models by our team or others that have been released over the past 5 years since we released that original OC20 data set. All of these are trained on OC20, validated on OC20. Some of these are us, so DimeNet++ were us scaling DimeNet. Noisy Nodes was Google DeepMind. Graphormer was Microsoft Research Asia. GemNetOC was a summer intern in our group. Electroformer V2 was an intern from Tess Schmidt's group at MIT. And so what we've seen is over the past 5 years, every year the models get 5 or 10% better with the same data. And so the things that are really cool now that I'm going to talk about for the next 10 minutes are all basically the product of just continued steady improvements in the model architecture and the data sets. And there wasn't one model that just changed everything. Again, what we're seeing is just really, really steady improvement, and I expect that improvement to continue, which is really exciting. But we're also still not there even with Electroformer V2. So as of today, we have released many different data sets, not just in catalysis. This is a electrocatalytic seminar, so I'm not going to talk about most of these other data sets, but just want to point out if anyone else is excited about these areas. There's heterogeneous catalysis, metal organic frameworks, inorganic materials, and then a small molecule organic electrolyte data set. This molecular data set is actually very similar to the sorts of properties you might calculate for solubility or viscosity that Nidhi was just talking about. So we sort of have the interfaces, and we also have what might happen out in the bulk, and both of those might be important for electrochemistry. And then we also have all these different models, including this UMA. And then I'm going to talk a little bit about some of the cool new data sets that we've released very recently. One other thing to highlight In each of these areas, the data sets that we've released are among the largest in the world in that area. In total, it's been well over 10 billion core hours of compute now. So just to give you a sense of scale, that's like tens of thousands of servers running 24/7 for a year. It's like going to the DOE and saying, I want an entire supercomputer for a year to build one of these data sets, just to like give you an idea of what makes these models so powerful. And it's really the data. Okay, the models that are available, the most recent one we released, trained on all these different data sets, is called the Universal Model for Atoms. I'm not going to go into details. I will just say this link works. So fb.me/fairchemdemo. There's a little Hugging Face website. You can run little calculations. I'm just going to run a little optimization. This is doing a optimization of this transition metal complex. You can upload your own structures if you want. The model's free to download. Obviously, we want you to actually run this on your own computers. This demo site is really just to help you understand the levels of theory, what is it doing, how to trust it or not, what are the settings that you need, does it work for your system? There's some other cool examples here of like, let me see, um, different spin multiplicity. So again, something else also related to electrochemistry, neutral ethylene carbonate, which is like the precursor for the battery SEI formation, very stable, but our models understand charge now. So you give it an extra electron, and all of a sudden this thing becomes very reactive and breaks apart. These are things that we know happen in real life, and now the ML potentials are able to help us capture this. Again, this is really only because of the data. We sampled enough organic species and with positive and negative charges and everything else that we can capture this sort of change in the underlying machine learning potentials. So go and play around with it. If you have any questions about the demo, feel free to send me an email or post a GitHub issue or whatever you want. A couple of things have happened since UMA came out, and we've been looking at the different results. And I just want to highlight how cool some of these models are in the day-to-day now. So as one example, again, going back to sorts of properties that Nidhi was talking about, this is just organic species in vacuum, so just organic things, no interfaces. These are all different DFT functionals that are quite popular in the community. Everything here is referenced to coupled cluster calculations. At the top, we have omega B97M-V, which is quite a fancy level of theory. That's the one that went into this OML data set. Down here, we have B3-lip. You all probably remember that if you ever did like a Gaussian tutorial as an undergrad. B3-lip was the standard thing you did to play around with water in order to get a sense of what was happening. And before we had OML, for example, the models that were available for organic species were okay, but they weren't amazing. So, for example, our models trained on the SPICE data set, which was also super cool and ahead of its time, or AIMNet2 or MESOF, they were not so far from coupled cluster, but they were not as good as the underlying DFT calculations. Another approach you could take is use fancy type binding methods. So Stefan Grimmer's group in Germany has this GXTB method, which is really, really impressive given that it's all physics-based. Super, super cool method. Getting closer to coupled cluster accuracy. But what really blew our minds was that the latest models trained on this OML data set that I was talking about are basically indistinguishable now from the underlying level of theory. They're just a little bit worse. And we're starting to get to the point where these machine learning potentials that are working out of the box, sort of generalizable, they are themselves better than many levels of DFT. So for example, if you're running B3-lip calculations, stop, right? Just use a machine learning potential trained on a fancier level of theory. That is unbelievable that we've gotten to that point. And it's not going to work this well all the time. You have to be careful. Like whenever you're doing research, it's on the users to understand the tools and the edge cases and when you need to be careful. So these aren't magic, but we are getting to the point where we can do real science. If we go to adsorption energies, like I mentioned at the beginning, this latest UMA model is getting quite good. So I would say we have essentially solved the problem for small molecules sitting on relatively simple metal interfaces. But we were also talking about electrochemical CO2 reduction, and that is not things in the gas phase. So one thing we've done in the past few months, working with Joel Varley at Livermore and Nitish, who just started his faculty career in Singapore, and Joe Gauthier at Texas Tech, is we released a new data set called OC25, where we explicitly added explicit solvent and cations to interfaces. This is an example of a little OCCO molecule, like you might think of in the middle of a CO2 electroreduction pathway on a copper surface. This is an MD run off of one of the machine learning potentials that we trained. Um, like the other data sets, very random, whole periodic table, lots of different solvation environments, different solvents, different cations. We basically threw it all together. The models are currently available. The ones that are available on Hugging Face right now are only trained on OC25, so those are the models you can download. We're going to have an update to the UMA coming soon that will also have OC25 support, so just one of the toggles will be OC25 or OC20 or OMOL. I should mention that, as Nidhi also discussed, electrochemical interfaces are hard. We weren't able to solve all the problems here. This is a first stab, so I just want to be upfront with like all of the things that we need to be careful about here. So first of all, the machine learning potentials are only as good as the underlying DFT, and the underlying DFT is still tricky. And so many people are trying to figure out ways of doing grand canonical DFT for constant potential calculations. So we did not do that. These are just neutral calculations in VASP. Second, if you're doing a neutral calculation with cations, effectively electrons go from the solvation environment to the metal based on the work function and the electron affinity and everything else. So effectively, you have an applied potential. And if you know what that is by looking at the work function, you can figure out what is the effective potential and then how does that relate to the catalytic mechanism you're interested in. But you need to do a little bit of additional analysis. It's not like there is an electric field that you're putting in as an input to the model that allows you to tune the reactivity. And the third major limitation is that pH dependence and explicit impact of applied potential, like at different orientations or oscillating. I know that dynamic catalysis is very exciting right now in this area. If you want a sinusoid on your electric field, I'm sorry, I don't know how to do it with our models right now. So you just need to be a little bit careful. But it's not all doom and gloom, right? What is in scope is if you want to understand electrolyte effects, cation, anion concentrations, and so on various intermediates in your electrochemical pathway, or for thermocatalytic reaction steps like this OCCO dimerization, the models are quite cool and helpful, and I think we can do some cool science. You just like can't do all the science we want to do. The models are also working better than we expected. So these are just a couple of the test splits we have. So for example, solvents that have not been seen by the model, the force errors are looking pretty good here. Ions that have not been seen, different concentrations, also looking pretty good. Zero point 0.1 EV for an entire system is pretty impressive, right? That's like a big system, a lot of atoms in a box. The forces are milli-EV per atom, order 10 milli-EV, 20 milli-EV per atom. You can do a lot of science with that. Same thing with different solvation environments. So this is the model that is currently, these are the models that are currently available. And then we'll have models like this. This was a UMA model that was fine-tuned on OC25, and then we'll have another UMA model that just has that as part of the pre-training too. Okay, so wrapping up, my overview of where we are for heterogeneous catalysis, starting from very simple things and getting to complex ones. We can do complex metal interfaces if you have like steps or edges or terraces or intermetallics. I think that's not perfect, but all relatively straightforward now. We can do small molecule adsorbates and gas phase reactions, and I would say the models got pretty good at that as of about 2024. Again, not perfect, but just you can do science now. Coverage effects as of 2025, we added that when we trained UMA last May. Things are getting a little better. Like I mentioned, thermocatalytic reactions and explicit solvent, not solved, but you can do science there. And the things that are still top of mind for us that we know are missing but are still tricky, electrochemical reactions and applied potentials, as I mentioned, support effects, so metal things on a oxide support or another metal interface. There aren't too many data sets that have that sort of data distribution, so we've been thinking about that a little bit. Explicitly modeling these on nanoparticles or nanoclusters themselves. Actually, I think the models could probably do a reasonable job here. I just don't think people have tried it yet. But I don't see any reason that the model shouldn't understand reactivity, given that they're all sort of local environment based. And then finally, the last sort of limitation, complex spin polarization, even in the inorganic materials data sets like Materials Project, sampling all of the possible spin configurations is hard. And so if you're doing really, really interesting magnetic catalysts, you still need to be a little bit careful in that too. I think we're going to see progress on all of these. These are like sort of obvious follow-ups. But again, if you're in this space, just be a little bit careful. It's not to say the models aren't useful. You could probably also take the models and then fine-tune them on a small data set if these are things you care about. But again, you just need to be a little bit careful. So wrapping up, we have an awesome team at Meta. We all sit downtown in San Francisco. If any of you visit San Francisco and want to come by for lunch, happy to host you. We're hiring. We have positions from junior to senior, mostly focused on the machine learning side, generative models, MD, things like that. I'm lucky to work at a place where there's not that many chemistry groups. So if you just go to Meta Careers website and type in chemistry or fair chemistry, you'll find us. So that's all I have. Happy to answer any questions. Thanks.
Thanks, Dr. Ulysses, and thanks to both of you, Dr. Ulysses and Dr. Rajput, for the excellent talks. And thank you for joining our webinar series today. So we will go ahead and open it up for questions. We have maybe 15 minutes. I think we can open it up to both speakers, so questions for either speaker. Just maybe specify who your question is for, or if it's for both speakers. So please, anyone with questions, feel free to raise a hand or unmute and ask. Otherwise, I will ask questions, and I have lots of questions. Okay, maybe I'll get us started. Just a quick question to maybe both of you. I assume that the machine learning is always limited to the accuracy of the underlying approach. And Zach, you made a comment about being benchmarked against coupled cluster. What does that look like for catalysis? Can we benchmark against coupled cluster when we have extended surfaces? Are we training the machine learning on less accurate functionals because that's what we can use for extended surfaces, or is there some other approach? What is that? I guess my question is the error relative to experiment harder or worse in the catalysis space than for, say, a small molecule in the gas phase?
I think catalysts are way harder, right? Because everything has to go right. In the molecular space, and again, I mentioned hybrid functionals like omega B97 M-V, like they're not perfect, but they are pretty darn good. And if you want to do couple cluster, it's also not that expensive. There's not that many electrons. Like you can't even imagine training on just couple cluster data directly in that area. In heterogeneous catalyst systems, the models also have to work for metals. And so then you get into plane wave versus orbital codes or Gaussian basis sets, things get more tricky. Um, there are people who are thinking about fancier methods. So like if you're doing oxides and strongly correlated systems, you might do a fancier DFT calculation. Um, the best case, like I know that there was some excitement for RPA calculations as maybe something closer to ground truth.
Mm-hmm.
There's been a little bit of work on coupled cluster for metals and extended systems, like a couple of
Okay.
papers in that space. But I don't get the impression that they've been tested enough on enough different materials to know like how well they'll converge and how accurate or not they'll be across many diverse systems. I think they're still focused on relatively small model systems that they understand well
Right.
before they scale up to the complex ones. But Nidhi, if you have a better suggestion on what we should be doing, yeah, feel free to jump in.
That's a great question, yeah, and I think I completely agree with what Jack said. And I think on top of that, I am well, I guess we also need to do much better comparison with the experimental results by advancing, spectroscopic analysis techniques where we can computationally predict these different solvation environment and reaction mechanism and then validate it experimentally and perhaps, yeah, perhaps, maybe incorporate findings from those comparison, let's say NMR or Raman into the training machine learning model, if that's an option.
Sure. Okay, any questions from the audience? Also, please feel free to type into the chat and I can read that out. I see there's a question here. I'm curious, how do you see, this is a question to Dr. Ulysses. I'm curious, how do you see these generalizable machine learning models handling constant potential conditions rather than constant or fixed charge conditions?
Yeah, I think that's a super interesting question. I think some of it starts with the data, right? And I would preface all this with saying if it's unclear what the right thing to do is with the ab initio method, like put aside all the machine learning. You just say like, I have all the compute resources in the world. I just want to do the right thing with DFT, how to do it. One thing that makes me a little bit nervous about this space is that there's several different competing methods right now on how to apply those things and how to screen, like solvated jellium versus grand canonical DFT versus others. And so I don't think I'm the right person in the world to solve those underlying problems. Like there needs to be the community needs to agree on what is the right thing to do to match experiments, and then we can think about how to build machine learning models. So we've sort of been waiting for that a little bit. That said, the models are starting to have more and more inputs. So, for example, for this OML data set, there's now an input on the total charge that's new for machine learning potentials. So you can start to imagine how you might have these other inputs that would allow you to model these things. How you incorporate local charge, localization, electrostatic effects, that's also moving very quickly. We've seen some progress in the past year, but it's still a little bit of a research question. So that's a long-winded way of saying like it needs to be the data and it also needs the model architectures. The data is the one I'm most worried about because those are the things that move much slower because you have to be very careful and the underlying theory is very hard. I'm pretty sure if we have the right data sets, the model architectures will catch up relatively quickly.
I think there's
There,
another question in the chat window. Chat
yes.
video.
Again, another question for Professor Ulysses. How can we ensure the data used to train the machine learning model for electrochemical interfaces accurately captures all possible interactions or configurations at the interface? So kind of similar to the previous question.
I don't know how to guarantee it, right? I mean, you can do some rough uncertainty analysis and try and say like how close is your new system to something in the data set, or you train a few models and then look at the distribution and see how does it work for something new to see is it like well captured or not. Um, Frankly, the strategy we do is we try to be as broad as possible and just throw as many things in. And random sampling of a large space is like not a terrible strategy for really, really large high dimensional systems. Um, that's also a good point of we're not going to know that we have problems unless people like those on this call try it for the hard systems and then let us know if it works or it doesn't work. And so that's one of the reasons that we're doing this all open science is that like we can't handle every edge case with a team of 10 or 15 people. We need all of the domain experts to look at things, debug them, let us know, post GitHub issues, and then often that leads to another data set or a bug fix or something else. If we're systematically missing a class of materials, we should just like generate more data in that space. But again, we don't know until someone helps us understand what we're missing.
Sure. There's a question for Professor Rajput. Is there a benefit to having less viscous solvents for CO2 electroreduction, or are there different use cases for less viscous solvents compared to more viscous ones? Also, a separate question, is the next step to also look at polyprotic acids as well?
Well, I think, from our intuition, we already know that as we decrease the viscosity, we are definitely, decreasing the barrier for mass transport, which is desirable for many electrochemical energy storage system, be it batteries, supercapacitors, or carbon dioxide electroreduction. So that's a common design rule. However, with that being said, from our finding of single solvents, we found all the good features were coming out from these aprotic solvents. But we know that we cannot just have aprotic solvent. We need to have proton donors. The protic solvents really help us in stabilizing the the interfaces. So based on my understanding from other electrochemical energy systems as well, I don't think a single solvent could be a winner here. We need to look for more complex systems and get a better understanding of the molecular interactions among, binary or tertiary solvent mixture along with the additives. So I guess the question was if lower viscosity is desirable. Yes, To answer that question, yes, but sometimes we do have to choose solvents for their other benefits, which have high viscosity, and to compensate that higher viscosity, we need to add something else in.
Sure. Okay, a question for Dr. Ulysses. Are there any plans to incorporate charge density derived observables like the density of states or charge partitioning either as training targets or auxiliary supervision in fair chem models? I'm curious whether that could improve transferability or interpretability for catalytic systems.
I know other people in the community have tried some things like this. We're open to the idea. I haven't seen super strong evidence that it was necessary, but I could believe it. One way to prove or disprove things like this is the molecular data set we released, OMOL 25, that was 100 million calculations across different electrolytes, small molecules, protein fragments, DNA. Again, that was the organic transition metal complexes, things like that. Um, we released the data set which had the energies and forces, but we also kept all of the raw electronic structure data, including the full electron densities, Fock matrices, every output from Orca that we could think of. The total data set for that is 5,000 terabytes of data that we saved from that campaign. And the first 4% of that data, 500 terabytes, is available at Argonne now. So if you search for OMOL 25 electronic structure data, that's available for you to download. And if the community finds the first 4% useful, we'll like try to find a way to host the rest of it. But like, I've never been in a cluster that has 5,000 terabytes of space for a data set, right? That is a serious, serious data. So what I would suggest is prove that it works or doesn't work in the molecular space, also where the systems are a little bit smaller and the theory is a little bit more well understood. And then maybe based off of that, we'll have an understanding of what to do on the systems like catalysts and things like that. But that data that's available right now is a gold mine. It's just too early. We only just released it last September, so we're waiting to see. We have one paper from our group where we try to predict the Fock matrix, but even we were only able to train on 50,000 out of 100 million because it's just like too much data to load during training.
Sure. We have another question here. I think this is for both speakers. It says, thank you for the nice presentations. A question from Ahiris Karantrantos, a senior scientist from Luxembourg Institute of Science and Technology. Are there any efforts using machine learning potentials to predict ion transport in electrolytes? Secondly, any research work with machine learning potentials to predict polymer properties like conformations or glass transition or other properties?
Yeah, I can take that. Ion transport and electrolytes, I think that's definitely in domain for OMOL. So give it a shot. I don't have a paper off the top of my head, but I don't see any reason that it wouldn't work. You should give it, yeah. If it doesn't work, let us know. If it does work, also let us know. I'd like to know that too. But also for the polymer properties, again, the organic data set OMOL has seen a bunch of polymers and proteins and things, and we released a polymer update in December, Open Polymers 2026. Microsoft had a paper, Polysym, that showed that a lot of these ML potentials were already working quite well, including ours for things like the TG. So short answer is yes, I think we are now there where we can start to do it. There is one caveat, though, that the machine learning potentials that I talked about are fast compared to DFT, but they are slow compared to classical potentials because these things, instead of having like a couple of hundred fitted parameters, they have like 200 million. So that's just like hard to evaluate. And so it's not going to be the same speed as the classical polymer simulations that you're used to. And so the real low-hanging fruit right now on the science side is anything where you want to have ions moving around in a polymer, like a membrane or some sort of electrochemical, like Nafion or something. I think that would be super cool. Anything where you're breaking bonds, like polymer degradation or upcycling or reactivity, things that classical potentials can't do. That's also just like waiting for people to do cool stuff. TG, like I think the model should do it, but it's not going to be the same. The delta is going to be smaller because the classical potentials are already sort of okay as long as you're not doing anything super fancy. Nidhi, do you have any other thoughts?
No, I just want to add one more reference. So again, Zach's group and a few other groups are doing a lot of interested work for developing machine learning potentials for polymers. But if you're just interested in macroscopic properties prediction for polymers, Professor Ramprasad's group at Georgia Tech has also done a lot of good work in that area and have multiple open source data sets if you are interested in just looking at properties and maybe what you're looking is already out there.
Yeah, he also had a nice paper doing ab initio calculations and on-the-fly potentials to sort of show that DFT can capture things like TG. Yeah, I
Yeah.
really like that paper.
Yeah, I think this has been a great discussion of, we have to definitely keep in mind, what can we do already with traditional approaches, classical approaches? What do we understand from ab initio approaches so far? What is that going to do, when we try and use machine learning to train against that? These are all questions that we all have to think about kind of holistically when we start looking at machine learning. I think just to stay on time, I think we'll end the questions there. I just want to take a moment to thank the speakers again for their excellent presentations, very, very interesting work, and thank all of the attendees for joining and for the very interesting questions. I probably forgot to introduce myself. I'm Ian McCrum, an assistant professor at the City College of New York, and a member of DC-MUSE. So again, I will just briefly share our slide here. Please do consider joining for our future webinars. Please do follow our LinkedIn page on LinkedIn so you get updates about our webinars and what the folks in our community are doing. And again, thanks to our speakers and thanks to all of you for joining. We really appreciate it.
Thank you so much, Ian. I just want to add one note. Somebody messaged me that my slides were a little bit blurry. I don't know why that happened because they looked fine at my end. And if you could not see anything and if there were any questions that you couldn't ask during the presentation, during this session, please feel free to email us and I will be happy to answer any questions. Thank you so much again for the opportunity to share our work.
Sure. Thanks, Nidhi.
Thanks all.
Thank you, Jack. Thanks, everyone.